So we are back. Last time we did some platonic solids. We studied symmetry of platonic solids, and we also saw certain graphs, Cayley graphs. You remember I tried to draw the Cayley graph of free group with two generators. Here is a nice picture. I got it from Wikimedia, and the key thing is that there are no circuits here. There are no closed loops. In this, just 1 minute. Sorry, I should have put it. Should have started. So there are no closed loops in this. We shall play with Cayley graphs after some time, and as you can see, this as an object, as a geometric object, it's a 2D object. It has certain symmetry. What kind of symmetries? For example, if you rotate it by 90 degree, there is a symmetry. If you reflect it about, say, one of the axis, say y axis, there is a reflection symmetry, and there could be more symmetries in this. I am going to show you certain two-dimensional objects, certain pictures which have beautiful symmetry. You can see that, right? Very nice pictures. Quite fascinating. Some of them are very classic. They are found all across the world in various monuments. Our own Taj Mahal is a beautiful example of symmetry. See this? There are so many. There are so many of them. Very simple one. So how to understand symmetry in two dimension? In R2. R2 is plane, real 2D plane, and how to understand symmetry? How many symmetries are there? All those are questions. Or if I ask you to look at one of these pictures, say this one, and I ask you how many symmetries does it have? Another interesting question that I can ask here is wallpaper symmetry. You have seen all the wallpapers which are there. There is tiling with those wallpapers. You can also use them as flooring, for the flooring of the surface of the floor using certain tiles, maybe something like this. So what are the different types of tiles one can actually make so that they can complete the wallpaper or the tiling pattern? That's an interesting question. So question is, how many different types of tilings? So one has to understand what's the meaning of different types of tilings are there. Interesting question. Before I answer all these questions, let me just talk of certain symmetries in R2. In fact, I will mention all types of symmetries in R2, and as you can guess, there are infinitely many symmetries. Okay, let me see. let me first define certain types of symmetries. You are aware of rotations, say rotations by any degree theta, and then reflection about a line, say y is equal to mx plus c. I hope you remember equation of line. M is a slope. What else? Translations. The translations, I'm going to talk about translations, and then there is very interesting type of symmetry which is there quite a lot in nature, which is called guide reflection. So I'm going to talk about all these 4 types of symmetries: rotations, reflection, translations, and guide reflections. And as you would recall, in one of the earlier lectures I had mentioned that composition of 2 symmetries is again a symmetry. Composition of symmetries is again a symmetry. So what should be all possible symmetries of R2? They should be compositions of what I have written here. Yeah, I am going to explain one by one what all these symmetries are, particularly glide reflection, which probably you might not have heard of. Before I start, I would like to show you some interesting artwork. This one is a beautiful artwork on a plate, the Russian style of painting. And can you observe certain symmetry here? Well, if I just rotate by 180 degree, there is a symmetry. Can you observe any other symmetry in this? Well, that's all. That's the only symmetry it is having, rotation by 180 degree. Quite beautiful. And making such artwork is, I'm sure, quite difficult thing. Want to see again this, and I'll just rotate by 180 degree. Same. You remember once I told what is symmetry? Here I am showing you, and then on my back I am doing something. And if I show you and it looks like same, so that you can't detect what was done or what was not done, that is symmetry. So doing something that you can't detect is symmetry. Rotation, as you know, I can, this R2 this is just for reference. Every point is same as any other point. When we talk of R2 as a geometric object, any 2 points are same. There is no reason for us to distinguish 2 points. So what is rotation? I pick a point P and then I decide an angle theta, certain angle theta, say, and I rotate everything by an angle theta about P by angle theta. So one can express all this in terms of matrix or in terms of matrix. So if P is origin, then I can express rotation as a matrix. So if P is origin, then rotation matrix, rotation by theta, is having very nice expression. It is equivalent to just multiplication by this matrix cos theta minus sin theta, sin theta, cos theta. So what is the meaning? The meaning is, if I have a point xy, so I am writing it as a column, is a point in R2, then if we rotate this point about origin by an angle theta, the answer is simply matrix multiplication of cos theta minus sin theta cos theta with this column matrix xy. As you recall, matrix multiplication, I multiply this row with this column, so this is x cos theta minus y sin theta, and then I have x sin theta plus y cos theta. So that's this new coordinate. So rotation matrices can be used to express rotations. So rotation is simply, as I am saying, you have this, you fix a point, just rotate. As simple as that. You are already aware of that. And then we have reflections, right? So for reflections, what do? We pick a line and we so here is R2 just for reference. I pick any line, say y is equal to mx plus c, and then reflect about this line. If there is a point P here, I just, and suppose this is 90 degree, distance is d, I further go by distance of d, and that's all. There's a point P dash. So I can reflect my points in R2, and again you can use certain kind of matrix to understand reflections. If the point, if the line passes through origin, so if C is 0, that is line of reflection. Line of reflection is just this mirror. So you can think of it as a mirror, right? If C is 0, then that is the line of reflection passes through origin. Then one can actually write then the matrix actually represents reflection. It's not very difficult to find out. Again, in terms of cos theta and sin theta. So for example, suppose this is our mirror, there is a mirror line through which we are supposed to find reflections, and suppose this is a point, say P. Let me write this point P as, say, cos alpha, sin alpha. I am just taking the point to be on a unit circle, or maybe let me simply write it r cos alpha, r sin alpha, so that this is alpha angle and the distance of point P from origin is r, and suppose this is line y is equal to mx, then this angle is theta, so m is actually just tan theta. And then for reflection, what we are supposed to do, this is angle theta minus alpha, so we have to go further by angle theta minus alpha and see what happens to this point. So, because for reflection this angle theta minus alpha will be same as this angle theta minus alpha, and then see what happens. So, that is not very difficult. Find this, and this matrix is actually going to be in terms of cos 2 theta and sin 2 theta. So, matrix of reflection is also there. The translation is easier thing. I have something here. I am just translating it. A similar shape. Just assume that drawing is okay. So, this is suppose distance r, further distance r, further distance r, like this. So, the same pattern is being passed on to via distance r, that is translation. So, I can do translation by any number, any distance r, any r. So, there are infinitely many translations, and then there is quite interesting one which is called guide reflection. What is that? It is a composition of reflection and translation. Okay, so here is some object. Let's take this one, some object. I translate it and then I reflect it. Let me take some other color. I translate it and then I reflect it. Something. So, suppose this object is x dash. So, x dash is glide reflection of x. This kind of pattern is observed in leaves, and then it goes like this, and so on. It's quite natural actually. Have you seen the footprints when you walk? Suppose you are walking on a muddy road, the way your footprints are there, see, they actually form a glide reflection pattern. So, left leg and right leg, their imprints, their footprints are actually glide reflections of each other. So, as you are walking, your one leg is here, other leg is here, and then next leg is here, next leg is here, like this. So, that pattern is glide reflection. So, very natural. So, when you walk, then you have glide reflection. So, 4 types of symmetries we have seen: glide reflection, translation, reflection and rotation. And then you can compose them, right? And there are so many possibilities. Compose them all. So, which ones? Rotation, reflection, translation and glide reflection. Compose them all. So, there could be some more complicated things. So, how many of these are there? Rotation you can do by any angle, reflection you can again reflect by any line, translation by any amount you can do, and in glide reflection again you can pick any axis of reflection and any amount by which you will be translating. So, this is an infinite collection. So what you have is actually infinite group, and you may expect that there are some complicated patterns out there. Say for example, I can rotate by certain angle, say theta, then I can compose by certain reflection by certain line, and then I can do certain glide reflection, and then I can rotate again. I can make life more complicated. So life could be more complicated, right? I can have lots of compositions, rotation, reflection, glide reflection, and now rotation, and then further maybe some translation. What is interesting is you don't get anything new. What is the output of this is either a single rotation or a single reflection or a single translation or a single glide reflection, and that's amazing. So there are only two, therefore there are only 4 types of symmetries which I have already mentioned, and that's a theorem, that's a serious theorem. So what's the theorem? Only 4 types of symmetries are there in R2. So when I talk of symmetries here, I mean isometries, right? So here isometries meaning distance preserving maps. If I have 2 points x and y, after performing one of these symmetric operations, the distance should be preserved. So if x goes to x dash, y goes to y dash, then the distance of x dash and y dash, distance of x dash and y dash is same as distance of x and y, distance between x and y. So that's the theorem. There are only 4 types of symmetries in R2. And now let's have some fun. I have shown you all these cards, right? There are so many of them. What you can do is you can try to identify what symmetries, what symmetric patterns do they exhibit. Let me show you one. This one. Would you like this as one of the wallpapers in your room? Does it exhibit extraordinary symmetry? Well, not quite. Probably you would like something like this as a wallpaper pattern, as your wallpaper. This has more symmetry. So what do I mean by that? So in fact, on the basis of symmetry, one can classify all these possibilities, whatever are the wallpaper patterns, into certain numbers, and that number I am going to tell you later. So let's discuss what kind of symmetries are there in. So there are the wallpaper symmetries or 2D crystal symmetries. Take this one. I mentioned 4 types of symmetries. Which one do you observe here? Only translational, right? So there are various names of these symmetries. So this is called P1. P1 is the pattern where only translational symmetries are there. Not much interest. Here is another one. Let me show you. This one. This is called P4. What does P4 has? P4 has two rotation axes, or maybe I should call center. This 90°. So what are the rotation centers here? 90°. If I pick the center of this and then I rotate, that is one. Or I can actually pick the center of this one and then I can rotate. Now you imagine not just this square getting rotated, but assume that there is a wallpaper. So you have this, or there is a tiling, you have this, and then there is similar tile here, similar tile everywhere. And then what is being rotated is the whole pattern. Okay, the symmetry operation is happening over the whole system, the whole wallpaper. So I can take this and I can rotate the whole wallpaper system about this. Again you get a symmetry. So there are two centers, this one and this one. Both are two rotation centers, 90°. And then there is one rotation center which is of 180°. Can you identify that 180° center? Well, that is somewhere here on the edge. You take this, rotate the whole wallpaper side, rotate the whole wallpaper pattern by 180°. So when a wallpaper or a single tile observes this kind of property, this kind of phenomena, that with similar kind of tile you just complete the wallpaper pattern and then observe that there are two rotation centers of 90° and one rotation center of 180° and there is no other symmetry, then we call this type P4. The one with only translational symmetry is called P1. Let me show you a few more. This one. So this is an example of what is called P3 wallpaper symmetry, and what is going to keep it symmetric or keep the whole wallpaper pattern symmetric? There are actually three centers of rotation. And they are by 120°. Which one are those? Can you identify? Well, you take the hexagon, take the center of the hexagon, rotate, or you take center of the red triangle, rotate, or you take the center of the green triangle and then rotate. So there are three types of centers of rotation and they are by 120°. So that is called P3 symmetry. And then there is this one, and the name is PG. Just the name. What does it have? Can you observe carefully? So this has, show you, glide reflections only. Just carefully look at it. Glide reflection, as you recall, is a combination, is a composition of reflection and translation. So it has only glide reflections and that is type PG. Now I have so many of these, right? I have shown you, I have so many of these, all these. And we have seen that there are infinitely many symmetries for R2. How many symmetries will there be for wallpaper patterns? That sounds interesting. So how many different? wallpaper symmetries. Different wallpapers meaning types of. The answer is quite interesting and it's not very easy. Very curious. So there are 17 different wallpaper patterns. There are 17 different types of tiles that you can make up to symmetry considerations. So who found all this and how did they find it? So this is Fedorov, and in 1891 he had observed all this, and then much famous person, many of you must have heard of him, George Polya, who in 1924 wrote an article on wallpaper symmetries. And a very nice reference for this is an article by R.L.E. Schwarzenberger, and this article appeared in Mathematical Gazette. Mathematical Gazette, volume 58. In fact, there are some higher dimension versions of this. And in higher dimensions, higher than 4, the question is still open that how many different wallpaper patterns are there, and higher dimension versions were kind of part of Hilbert's 18th problem. Those who know what Hilbert's problems are, in the year 1900 in Paris, Hilbert proposed 23 problems, and that was kind of his expectation from mathematicians for next 100 years, what he would like people to work upon. So he proposed 23 problems, and problem 18th has a portion where he is asking about higher dimensional versions of this theorem of Fedorov, which says that there are only 17 wallpaper patterns, and there are certain names. I can just mention some of those names. You have seen P1, P3, P4, PG, and then there are many. In fact, I'll just write all those names. P1, P1, P2, P3, P4, P6, PM, PG, CM, PMM, PMG, PGG, CMM, P4M, P4G, P3M1, P31M, P6M. I hope these are 16, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Yeah. And this nomenclature is according to what kind of symmetries do they exhibit. In fact, one can devise algorithms on how to determine what kind of wallpaper symmetry is there in one of the wallpapers, in one of the tiles. It's not very difficult to devise once you understand what all these symmetries are. So this time we talked about symmetry. Next time we are going to talk about one interesting software that is used to understand symmetry, that is used to understand groups, and we would make that software solve Rubik's Cube for us. So keep watching. Thank you.